Okay, now we know about reliability of electronic devices. We know how to analyze these. We know how to do some failure analysis. And now we go to the next step. So imagine we have a complex system, and such a system must be analyzed not only with respect to failure rate, but we need other information. For instance, we have to know if the system is safe, for instance. And so one of the most important analysis we can find is so-called risk analysis. What is that? Risk analysis, for that we must recall what risk is. Risk is some property which is defined by the probability of a failure multiplied with the severity of such phenomenon or such event. And here it is important, of course, when we have these two parameters, it's the quantitative aspect. So for instance, the failure rate or the failure probability. And it is the failure mode. That means what can happen, what can go wrong. And in that way, we have several analysis types. So risk analysis is the most crucial part when we have safety relevant systems. Such systems are in, for instance, in medical devices, in implants. These are in aerospace, aircraft. These are in automotive technology, especially now as we talk about autonomous driving. So in that case, there must be a risk analysis. And risk analysis, again, it helps us to find out what can go wrong, what is the cause of that, and what's the probability. And only after we have performed risk analysis, we can do risk management, that is how to deal with risks. So when we find a risk in autonomous driving, we have several options for risk management. We either could say we improve our system, we give it a more powerful computer, we use machine learning, or we say, no, there will be no autonomous driving. The driver still must be on the wheel, and he must still be present and attentive, so he can take action anytime. So risk management means what to do when you have analyzed a risk, but first of all, you must know that risk. So that risk analysis is more or less a complex method which has several steps also. And you cannot just have one risk analysis, you have to have many types of risk analysis, and that is the overview which we have. We can have, for instance, FMEA, that is failure mode and effects analysis. That is something which is used mainly qualitatively to find out what can go wrong. And it's a so-called inductive analysis because it's bottom-up analysis. And the deductive is top-down. We have that's not fault-free, that's fault-tree analysis, sorry. Then we have the failure rate, so we have so-called parts count and parts stress method. Parts count method just means you have a part which has a failure rate of, let's say, 100 fit, and another part which has 200 fit, and you just sum up all of the failure rates of all devices, and so you get a total failure rate. It's a quite primitive method, but it is also helpful because you can make a system safer, but if it's more complex, the failure rate will increase anyway. And then there are system state methods. So these methods help you in the detection of the evolution of some fault or failure, and mainly for systems where the state or where the system state can change between several possible states. For instance, you have a failure, you have a repair, you have another failure, another repair, and so on. So that are methods which show you more how failures can develop when there are several possibilities. Okay. But now let's make a deduction of, for instance, the parts count method. Imagine we have a printed wiring board, and on that printed wiring board we have a certain number of devices, and the printed wiring board assembly, it will fail when any of the devices will fail. So you can make an analogous model where you say, just in your imagination, all devices which are there are resistors, and all are switched in a series. And there is one current through this circuit, and when the circuit is broken on any of these locations, here it's just 3 locations, the circuit is broken and the device has failed. Of course, these are not real resistors, also the resistance doesn't matter, but what is relevant here is what is the reliability here. So you could say you have in some way some reliability parameters like R1, R2, R3, or we have lambda 1, lambda 2, lambda 3, and in that way we have we want to know data, for instance, the reliability of the system or the lambda of the system. And that means we must have an idea how we can compute this. And again, one possible description is the reliability probability or survival probability, which is just 1 minus the failure probability. And when we have 2 resistors in a series, which would be I and J, and J, then we could say the probability that of these 2 resistors in a series will be the reliability of 1 times the reliability of 2. So if the reliability that the first survives is 50%, and that the second also survives is 50% at that time, then the total system reliability will be the product of both, and it's the Ri multiplied with the Rj, or R1 times R2, and 50.5 times 0.5 is 0.25. So we take it a little more general. We can say the reliability of the system is the product of all reliability functions. And of course, we must say the reliability of time over time it goes down, and the system reliability at one time, it just multiplies these individual reliabilities, and so you get a system reliability which is significantly lower. Okay, in that way, of course, we can say that's just the reliability function. And I must say, one of the easiest way to do complex systems is either to address reliability function or to address failure function or to address both. So in that case, we would like to know the failure function of a certain element. So Fe is 1 minus Ri of t, and that in the case of an exponential distribution, it is 1 minus e to the power of minus lambda times t. Typically, when times are very short, for instance, when the time is roughly 1% of the inverse of the failure rate, then you can do an approximation that you say the failure function or the total portion failed is just the failure rate times time. If it is a longer time, you must take this explicit formula. So the reliability, as we have seen, is e to the power of minus lambda e times t. And now we put that in this product formula. And the system reliability is the product of all e to the power of minus lambda e t. On the other hand, we could say, we can modify it. Rs of t is e to the power of minus sum of all lambda e t, that's just simple mathematics, times t. And when you replace this sum of all lambda e with a lambda s, you can end up with this formula. Rs is e to the power of minus lambda s times t. And just adding the individual failure rates, that's the so-called parts count method. Part count method is used when you take standard conditions for all devices. That means, for instance, for your printed wiring board, you say all is at 70 degrees centigrade, and you compute failure rates for that. When you look at it a little more, let's say, precisely, and you analyze the temperature for each individual device on your board. So possibly the processor has 125 degrees centigrade, and the resistor has only 80 degrees centigrade. That means you take the individual failure rate for each temperature, which exists here. That's the so-called parts stress method. Okay, in that way, we have first derived a solution in the case of a series system, and in that system where all devices must survive in order to have a functional system, we can add up all of the failure rates, assuming that we have an exponential distribution of failures. That means it's no systematic change of failure rate, like increasing failure rate or decreasing failure rate, but it's just failure by chance, and in that way, that's an important prerequisite. So I already said, parts count method is you add up all of the failure rates. Part stress is you add up all of the failure rates for the individual cases. In many other cases, you cannot assume a constant failure rate. And very often you can assume a Weibull distribution. Weibull distribution, as you know and have to know, f of t is 1 minus e to the power of t divided by tau to the power of beta. Beta is an exponent. If beta is larger than 1, it's increasing failure rate. When beta is lower than 1, it's decreasing failure rate. And tau is a characteristic lifetime. That's the value where 63% have failed. What you can show now is the following, that when you take the r of t as e minus t divided by tau to the power of beta, if all beta are equal, and only in this case, you can have an analytical solution. Otherwise, you must say the RS is the product of all of the individual complementary Weibull functions. And here you have to add up all of the t to the power of beta times 1 divided by tau to the power of beta. And that is quite complex because you have to know all of the beta. If all of the beta are equal, it will become more simple, because the characteristic lifetime of the system is just the sum. The inverse of the characteristic lifetime is just the inverse of the sum of all inverse values. And in that way, it is a possibility that you can compute the characteristic lifetime of a system. So that means, for instance, you have a characteristic lifetime of 1000 for each of both parts. Then it's 2 times 10 to the power of minus 3, and the inverse again is 500. Yeah, so just the inverse adds up, and in that way the characteristic lifetime is of course decreased. And in that way we have a method also to have something like a parts count method in case of a Weibull distribution, but only when the Weibull exponents are equal. Okay, that's for today. And what I was showing you was the most simple case, how we can compute reliability characteristics for systems. So it's series systems, and we either have to take the assumption that that in such systems we have exponential distribution, or we have Weibull distributions where the Weibull modulus is the same for all failing devices. Okay, for today I'm finished. Thanks for your attention and see you in